Welcome back. Let's go to our code again. So, just to recap where we're at, we've got our language, our basic Berliner language. This is our most basic example here. We've got an interpreter which will run all three examples. We have a compiler which compiles to assembly, and the program that it creates will run the first example here, which is amazing. I can probably get rid of this and still exit if there is an unknown token. There should be no unknown tokens at this point. Another thing that I fixed up between the last session and this session was this here. I went on and on about it last time. How it was doing this XOR of racks and racks, which I believe was just basically trying to set racks to 0. So I changed it to this more explicit, move 0 into racks. I feel like that's a lot clearer. I don't know if there's performance implications, maybe this is slightly slower. I think it's not a big deal. Definitely not in the context of this program. It's so simple. Another thing that I wanted to do, let's do this first. So I found out there's a way you can do like a procedure call in assembly. I didn't realize this was a thing, but we can go call, and then we just pass in a label, and then return, which will take us back here, and then we'll continue. So I guess the difference between a call and a jump, from what I didn't even read this properly, but the simple difference that I can see is that if you do a call, then you can follow it up by doing a return, and it will take you back to where you were before. Let's just have a look. In x86 NASM assembly, the call instruction uses to call a function. The function is typically labeled with a descriptive name, including its purpose. After the function is executed, the ret instruction returns the instruction immediately, or returns to the instruction immediately following the call. So it's just, I guess it's just a way of jumping to a label with the ability to go back to where you came from afterwards, which I think is great for us. The reason I wanted to try that is because we have this buffer string to int, which is basically a procedure, and we've done it in a way. If we go to the assembly, so it's part of our read. Part of our read is that we need to execute this procedure because it'll take the buffer, which contains the user input, and convert it to an int, which is what we want as part of our read. The problem is that here's that procedure once, and here's that procedure again. Like, we're just duplicating it. It's exactly the same. The only difference is that this one has underscore zeros in all its labels, and this one has underscore ones. And the reason we do that is because it's inline, It's basically, it's basically an inline function. So it'll execute these, then it'll execute the function, and then it just keeps going. And it does push, which is the rest of what we want to do as part of a read, and then it moves on to our next read. Uh, and because we have it like that, we can't be jumping like when we're in this one and we want to go back to the top of the loop, we can't jump to the top of this loop because now we're in the wrong part of the program. And for this reason, we have this function duplicated twice in our assembly. And sometimes that can be what you want. If it's a simple little function, and actually this is a simple little function, and you don't want the cost of calling a procedure, which I guess we'll get into soon, some of the basic a little cost, then you can inline it, which basically means just put it straight here. Don't do a function call to somewhere else, just do the thing right now. So I guess the downside is that your executable can be larger because you're repeating the same code multiple times. I don't like this. I don't know how to fix this in OBS. I'm a little bit out of sync. I'm going to try pausing. Okay. No, that looks even worse. I don't know what to do. Okay. I'm out of sync. It's terrible. I think it looks worse. Oh well. What to do? I really wish I could fix that. I guess I'll try and fix it in post and then cut this bit out. All right. So yeah, you can either have a larger executable without the cost of calling a procedure, or you can have a smaller executable where this is just occurs once, and the cost is, we'll get into the cost a bit later. Okay, so first let's see if we can turn this into a procedure. We don't really need to, but I'm curious, let's see how it works. After that, I actually want to look and see if there is, because quite often in languages, especially in low-level languages, there will be A to I, ATOI as a function. So I'm wondering if it translates to an assembly instruction, actually. I think A to I never really knew what it, I never knew why it was called that, but I think it's ASCII to int. I think that's what it means. So we'll see if we can find something like that. Maybe we can just replace this whole thing. And then there is a little bit left in our compiler to finish off the language. We need to push and add. And once we can push and add, then we should be able to run all the other two examples. So basically in this episode, let's see if we can finish off this compiler. All right, so if I go back to the browser, we can see this is how a function call happens. This is the most simple. So let's try that for now. Yeah, that should work if we just try that. So what we want to do is, instead of having this down here in a separate function, we can just put it, I think, at the end of our assembly. Yeah, because the way we have this language, I'm going to say this language requires explicit halts. That's how he's done it. There's always a halt. Oh, it's 3. Yeah, there's always a halt. So I'm going to say this language requires explicit halts. And the reason that matters right now is because then that means that if I put my function after the main body of the code, it should always be after a halt, which means that it's not just going to get executed at the end of the program by accident. You have to explicitly call it. Okay. So I guess we need to change to ampersand out now. Yeah. Because in our procedure it was already a pointer, but here it's not. And instead of this label, instead of this comment, I think we can just put the label, right? This is the name of the function, buffer string to int. And now this is the nice part. This is where we can just, instead of putting this index on the end, just cut all that out. So we have another label, which is the start of our loop. So the start of the function is just set this to 0. Now for now, and this is going to get into the cost later, for now we are making an assumption about RSI. We're assuming that RSI is where our buffer is. Yeah, we're assuming it's in the RSI register. So, or at least the address of the buffer is in there. So this is all fine, this is all fine. This here is another label which we put an index on the end of. Well, that's us jumping to the label, jumping to the end of the function. That's not needed anymore. We don't need to be able to jump to the end of the function. Instead, what we need to be able to do is return. Very useful comment here. The best kind of comment is the one that tells you what the code already tells you. So all of this looks good. And then we come to here. This is where we jump back to the start of the loop, jump to top of loop. And we don't need the index anymore. So it's just simplified it. It's just basically we've been able to take the indexes off of these because there's only one instance of this function now in the code. It's not one per it's not one per call. It's just one. So that's great. That means we can get rid of this. And then up here where we're calling it, now instead of calling it, we will do, here's the label, and we will say, where are we here? Call. Another great, another great comment. Okay. So yeah, it's basically exactly the same, except we're taking advantage of the call return. And the inputs to this function are kind of implicit. That's the thing that's not so great at the moment. This RSI is an input to the function, the buffer. And I guess also Rex is an implicit output. Yeah, so I guess you could sort of make a calling convention where you say the output is always in Rex. Yeah, I think that could be all right, except if your code beforehand is playing with Rex and afterhand still wants to play with Rex, you could interfere. I don't know assembly language well enough to know if that's the kind of thing that would happen, but anyway, let's just try our simple setup. If we go to the compiled code, now we see that our read is much more concise. You know, we do the syscall, which is reading from the console. Then we call this conversion, and we push the result to the stack. But you know, it's not very clear that this is the result of this call, and yeah, but it's much more concise. And then down after the end of the code, you know what? I'm gonna put a new line there to separate it. There. So this is the main body of the code, and then this is our function, which has a loop in it. And hey, we can't just we can't just blindly return like that. It's returning with a condition, right? Where did I jump to end? There it is. It's jump of equal to end. So we want like a conditional return. Ah, okay, that's getting interesting. I don't think he has anything like that. He just returns. So let's say x86 conditional return. Call subreturns conditionally. Conditional versus unconditional jumps. What is the conditional ret instruction? The conditional return call back to call instruction used to end the execution in a subroutine if the input logic is true. So let's Google this ret C x86 NASM maybe. New return, far return, don't know what that means. Why don't these two instructions simulate ret? Pop ECX, jump ECX. Ret, does it pop? Does it pop first? Transfers program control to a return address located on the top of the stack. The address is usually placed on the stack by a call instruction. Okay, so there's already a little cost. There's a push and a pop, which wouldn't have happened if we didn't have a function call. The optional source operand specifies the number of stack bytes to be released after the return address is popped. The default is none. This can be used to release parameters from the stack that were passed to the call procedure and no longer needed. Yeah. The ret instruction can be used to execute 3 different types of returns. A return to a calling procedure within the current code segment, located in a different segment. I still don't know how to do a conditional return. Ret C. So x86 NASM. return if equal. There's no written instruction I know of. NX86 issue, not a NASM issue, so you can do compare. Okay, you can do a comparison and then just jump past the routine, the return. Yeah, or sometimes you could have it jump to the end where there is a return. And then you can do a bit of cleanup at the same time. Yeah. Okay. Let's just do that. So in our code, because we only want to return if the check for the new line was true, how did we do that before? It was JE, I think, jump if equal. Yeah. So up here we want to go JE let's say ret. Put this down here and put a ret above it. Kind of like that. That's basically it. So if we do want to jump, then we jump to our ret label, which just calls ret. Okay, run that. Okay, that's what we have at the end. And then up here we just call it. So enough of that. Let's see whether it actually works. 5, 8, not equal. 44, 44, equal. Oh, we still need to figure this out. Why is it like cutting off the end, but here it's like extra? It seems like this is very strange. But that function call looked like it worked. I'm really, I'm really confused every time we just change some assembly and we still just get the output that we were expecting. I really don't expect it to just work, but it does. Okay, so now we have a procedure call. Now, in this little article, we can close these. In this little article this guy made, he's got the passing arguments. So here he's just putting them in some certain registers, and then I guess the function is assuming that there should be things in certain registers. That's how we're working at the moment. I think it's not the best. It's a bit too implicit. So there's also stack-based argument passing, where you push the arguments onto the stack, and then it acts on those arguments that are in the stack. He's got stack cleanup here, which I find a bit strange. I think just before the return, it would be nice to pop the arguments off and then maybe push the result on. So now we have the result. Yeah, let's try that. That way, yeah, so before we call, we want to push whatever it is the inputs to this function are. So let's say push RSI, you know, that's got the effective address of the buffer in RSI. So let's push that onto the stack. So arg0 let's just say call proc. So it's similar to that. It's quite similar to this. Here they've, well, that's interesting. Okay. This is the same thing really, isn't it? Except instead of call blah blah, it's just syscall. But they're saying their convention is, hey, put the stuff in these registers. These are the ones we know that we're going to act on. And then call us. So maybe I just copy that. So I'll move. I know I've just like totally changed my mind about everything. But we can't return to racks as well. No. Let's stay the course. Our arguments go on the stack. That's how we're doing it. So we push RSI onto the stack. That's arg0, that's our buffer. Then we call the proc. And we were saying that the return value we want to push onto the stack, which is actually exactly where we want it, right? That's this last line. So there's no need for us to do anything after because our calling convention is saying that the return value of a procedure should be pushed onto the stack. And that's exactly where we wanted it at the end of our read. So great. So we pushed our RSI onto the stack. Now we come into here. So just before our return, we should push racks, push return value to stack. Yeah, so this is the racks that we're creating all the way through. Great. Now the first thing we need to do, or the difference, should I say, instead of RSI, so okay, let's do it a simple way so far. Let's pop the top of the stack into RSI. Pop arg0. And then that should work the same as what we had before. 5.7 segmentation fault. So that did not work as before. That is how you do a pop, right? It's just a simple, I've done pops before. Yeah, just pop. Pop arg0 from stack. And RSI. So I mean, basically, we had it in RSI. We push RSI onto the stack. Then we pop back off the stack into RSI again. So RSI should have the same value that it had before. Unless we need to pop like keyword. That's right, can't debug because of that. So it's even before I press the 7. So that did seem to compile though, didn't it? It didn't complain. Yeah. But it's actually, it wouldn't complain at that step. It would complain. Let's try just calling the assembler. The assembler works, yeah. No, I guess everything works because we get up to the 5. Interesting. If we push and then pop the same thing, we're getting an error, but then there's also, we need to think about what we're doing here. Push rex return. Yeah, interesting. So this is basically two calls in a row. So it's this call followed by a prop call. And we get a segmentation fault, and it would be great if we got more info. I mean, I was saying before that I was surprised when it kept working. I think we've got lucky. I think we got lucky so far. Now we've got something that doesn't work, and how the fuck do we figure it out? It does say core dumped. Are we supposed to look at that and figure out what the hell that means? I guess this is also why, well, I don't know if that would help either, actually. I was going to say you can add debug symbols to the assembly, which basically maps it back to the source code. And that's how, if we did that, then, I mean, it gets a bit more complicated than that, I guess, but I guess the idea is that you could then set a breakpoint, and you would be able to break, and maybe it takes more than that to do that. Maybe adding the debug information just allows you to see, like, okay, what line of the source code were we executing instructions for when something went wrong. Okay, so if we were to comment out this procedure call, yeah, it's just going to say not equal for everything because it is not actually converting it to an int. So Rax just has 0. No, it's not that Rax has 0. It's that we. Interesting. Because it's popping off the stack, even though we never put anything on the stack. So it seems to be this push RSI, pop RSI that caused us the issue. Is that right? No. We still have an issue. So here we've loaded the effective address into RSI. We call this procedure buffer string to int, which is down here, buffer string to int. Setting Rax to 0. I'm using RSI and RDX. I think I like the idea of using RBX as a second register because, you know, A, B, C, D. Why jump straight to D? You know? I mean, these guys, I mean, I don't know where they're going. RAX, RDI, RSI, RDX. Beats me. But there is an RBX. We've got it right here. There is an RBX, right? Surely it would not compile if there was no RBX. RBX X86. Yeah, Rax, Ribix, Riddix, Rissy. So what is wrong then? We took out the push and the pop. It was working before. So this is obviously just the syscall. And then directly after we call our procedure. And our procedure at the end pushes racks. That's also something that I changed. Before it was pushing racks up here after the call. Is that something? Okay. Interesting. Just by moving that. So if it's after the call, I can push racks. Oh, I can't return. I can't return by pushing something on the stack because as we learned before, return pops off the stack to decide where to return to. And now it's trying to return to our return value. That doesn't work. Okay. Okay. So we pass in. I guess only if we get to a more advanced language, which I'm going to get to next time. We need to think this through a bit more. But right now, I think the convention can be that racks contains the return value of the stack of the call. Do we still want to push onto the stack? So if we push onto the stack and then we do a call, that's why I was wondering this before. That's why. Because, okay, so he pushes these two onto the stack, then does a call which does another push. I guess it pushes 4 bytes onto the stack, which means that if we want to get these two earlier pushes, this ESP is the top of the stack, and we're going +4 to get past that return address to this one, argument 1, and then we go another 4 bytes back to get to this. So this is argument 2, as he said. He doesn't really, well, ESP register H's. I don't think it actually says why you need to do that. It just does it. This, it's kind of this. I feel like this site is handy, but you need to take it with a grain of salt. Last time we had to like modify the code a lot to get it working. Okay, but so if we want to do stack-based arguments, let's push RSI onto the stack. And just for simplicity, we will continue to use RSI within the function. So we're going to pop. So how do you pop? You have to do a move because it's not a pop. So we need to move into RSI, RSP, which is our stack pointer, plus 4. Pop, retrieve arg0 from stack. Let's see what happens. Invalid combination of opcode and operands. Oh, probably need a comma here. How's that? Okay. Ooh, segmentation fault. Is it because we're using 64-bit register? Is that going to cause a problem? I think this is always going to be 4 bytes. Move into RSI, RSP plus 4. Or is he just wrong with his arithmetic here? So if we do RSP, it's actually like RSP and above. That makes sense. So if we go back for RSP plus 4 and above. You know what? Let's not worry about this. I think it's nice that we got the call working, but let's not worry about doing this push. I think that's good. Okay, that's good. You know, because we're already 42 minutes in. I think we did some good learning on that already. And I think it's nice to just like, okay, we learned a bit. We haven't like delved right down, but we got a bit deeper. Now let's move to something else. Next time we come across procedure calls, let's take a little bit more, you know, take another bite. So let's go back to our unimplemented operations. And this is going to be easy peasy. You know, add is just the same, except we do add. Boom. Done. That's it. And push. I mean, come on. Push. But what are we pushing? So actually push means we get a number afterwards. So it's kind of like this. We can say nothing to push. And then it's strings dot concatenate. And we'll push, but here instead of RBX, whoops, need to change my keyboard. We want to put in there the current token, which will be the 2. Push to stack, like that's it. Push is literally one line of assembly. So that shouldn't affect this program because it doesn't have any of those commands. But we can go to test case 2, which is odd or even. And now we have the push. We don't have add in here, but we have push. So let's test out push. Okay, we need a new configuration. Duplicate that one. 2, 2. Run that. and run it, and then 7, not looking good, not looking good. Do we have an infinite loop or something? So we have our read, which looks very familiar to what we were just working on. We have a jump if equal to 0. Looking at the top of the stack, should not be 0 because it was, well, we're pushing the result of, yeah, what was read in. So it was a 7. So it shouldn't be 0. So then we push 2. Then we subtract, we pop them back, do a subtract when we push. Then we check jump is 0 again, but it's not 0, is it? We subtracted 2, so we should get 5. Then we do another jump, we check if it's 0. So this could be optimized, I guess. If we have to, I feel like this has been duplicated. Just have a JZ and a JA. Anyway, jump if above 0, which 5 it is. So then we get push 2, subtract 2, we're down to 3. That's not 0, it's above 0. Subtract 2, so we're down to 1, not 0, above 0. Subtract 2, so we're down to -1, not 0, not above 0. Print string 0 and halt. String 0 is odd. It looks right to me. But it does seem a bit like it's caught in an infinite loop or something that's just continually going. Push 2. Do I have to say how big that is? Where did I have to do keyword with comp? Is there anywhere else where we have like just a literal like that? We have the zeros for comparison, and we're doing keyword. Maybe that's why we have to do keyword, because we don't know how big this is. Here we're moving the number 16 into a register, and that seems to work. But we know it's a 16-bit register. When we push, we don't know. So if I save that and run, I don't know if that's continuing to prompt me or if it's just because it's hanging, and that's just how the console looks when it's hanging. No, it can't be calling this again and again. This is the only place we have a read. This is called read. Only here. So it's only doing that once, that's for sure. Calling this, then it's pushing racks. Yeah, that makes sense. So if I was just to do like, instead of that, if I just did push 5, what happens? It hangs. Okay, That's interesting. Does it make a difference if I keyword it? Apparently not. Well, we're definitely not getting to here or here because we're not printing. This function is not getting called. You know, we could like cut that out and it would, you know, it's not like it failed to compile. So what if we cut out this part and we just do the jump, you know, if equal or we can't jump. Yeah, we either jump to L1. We never jump to loop because loop doesn't exist anymore. Well, no, we don't want to jump to loop. So we're testing if it's 0 or not. And we are reading. Okay. I thought this was just going to work. You know, I thought we'd done all the work on the other ones. So, yeah. So what did we cut out? We cut out this stuff. This seems to be where we're getting a problem. I guess maybe with this loop business. And I thought it might have been because of this push. x86 push. Whoops. Hey, why aren't you? X80. What the fuck? X. X. Oh my god. The hell is going on here? I just turn my keyboard off and on again or something because this is some crazy shit. What the actual fuck is going on here? My keyboard is not working. Okay. Is the program still running? No. Thought that somehow that might be causing an issue. Even if I try to use the keyboard on the laptop, I get the same issue. Doesn't work. Okay, I give up. We're done. We're done. We're nearly an hour, and this is just totally broken. I can't type. Sorry. Okay. So we had some madness just there. My keyboard stopped working. I got a bit frustrated. But then I watched back this video. I hadn't watched it in a while, and I forgot about it, to be honest. Where will it be? Here? So this is the compiler video that he did for this language that I'm borrowing from him. So I watched through some of it. He's using Windows syscalls, and for printing, he's calling the C printf function. So he's doing some things different to me. But one thing I found was for the string constants, he mentioned putting comma 0 at the end. So if I look at the output assembly here, there's comma 0, where before, I don't know if you remember, I'd been adding the size of this +1 because I just remember Fireship put a number there and I kind of figured out that it was equivalent to this +1, and I thought, okay, let's try it. I probably should look at the documentation, but I have not. But in this video, this guy said that to put a comma 0 to null terminate, to terminate the string with a 0, just how C strings work. I think it's called a null terminated string. So that's one thing that I figured out. Another thing, we were getting an infinite loop, and I wasn't sure what the cause was. I was playing with this push. I was thinking maybe I needed to put it in a register first and then push it, because then by putting it in a 64-bit register first, then maybe then the assembly or the assembler or CPU or whoever it is that's really involved in executing these things, then maybe that kind of gives the hint that it's a 64-bit number, because maybe that was causing issues if it was not. But that was not the case. The issue I found in the end, I found that it was not hanging for even numbers. It was only odd numbers that the issue came. So if we come back up here, so this is here. This is where it's doing the comparisons, right? So for even numbers, it would eventually come to here and jump, and that was fine. For odd numbers, we go down to -1, remember? And then it was doing this jump. And this used to be JA, jump above, which I'm still saying jump if above. Maybe I should change that to jump if greater, I guess. And the difference between JA and JG is that JA is for unsigned integers and JG is for signed integers. So because we were doing an unsigned comparison, the -1 would have wrapped around and become a very large number, which would then just keep looping, subtracting 2 until it got to negative again, which is a very large, it's just an infinite loop. But JG works. I think that's about it. It's all working. I haven't tried this program. I remember it should give a C. I don't want to do a whole bunch of tests with it. I think it would be sufficient if we compiled and ran it and we got a C, which we do. So I notice now with all of our prints that we're not getting a new line at the end, but we do get, for not equal, we actually get the full. It was equal, wasn't it? It was not showing the whole word. It was skipping the L. So we're getting the full word, but we're not getting a new line at the end. I tried putting at the end of the string constant a new line character, but I failed. Wait a minute. Wait a minute. Did Fireship put a 10 there? Remember, 10 is the new line character. 5, 8. That's why I put a 10. I was thinking, it's like some size or something, but it's really like, I guess when you're declaring this thing, you can have comma separated multiple things that come together and become this buffer. And because it's a special character, I guess assembly does not, you can't do /n. So you have to put a 10. All right, so that's another thing figured out actually. Well, I guess it's the same thing that I thought I had figured out, and now I figured out better. All right. So if we did 3 again, we should get a C with the new line. Yeah. Okay, great. I think that's basically it. I think we have succeeded in writing a compiler for this program. He also, I noticed in his video, he also made a pop. I'm not sure why. I remember this, no, it was the first one. I remember it had like manual pushes instead of reads. No, it was this one, wasn't it? Instead of a read, I think it had like push add. But I don't know, I don't think there was actually anywhere that had a manual pop. So I don't know why he was doing a manual pop. But that's it. That is our assembly, our compiler for Berlioz. We have succeeded. So that concludes this. Move on to a language that's a little more interesting next time.